Welcome to Statistics, where we bring complexity to clarity. I'm excited to have you join me for our 17th unit, Correlation. Let's begin our journey of correlation by understanding a few terms related to it. Beginning with univariate population. A population that is characterized by a single variable is termed as univariate population. Example, population of height of students, weight, yield, etc. Bivariate population. When two variables are simultaneously studied in a single population, it is termed as bivariate population. Example, the height and weight of the students, rainfall and yield, amount of fertilizer used and the crop yield. If two quantities vary in such a way that the movement of one is accompanied by the movements in the other, these quantities are said to be correlated. Example, price of commodities and amount demanded, increase in rainfall up to a point and production of crop. Thus, the degree of relationship between the variables under consideration is measured through the correlation analysis. Now let's see what do we mean by correlation. Correlation indicates the association between two or more variables in a bivariate distribution, or an analysis of covariation of two or more variables is usually called correlation. Correlation can be of different types, like positive and negative correlation, or simple partial and multiple correlation, or linear and non-linear correlation. Let's discuss them in detail. Let's see positive and negative correlation. Here in the graph you can see that there is positive correlation and r is greater than 0. We can notice that here variable x is increasing and simultaneously variable y is also increasing. Whereas in the second example, variable x is decreasing and simultaneously variable y is also decreasing. Thus, if both the variables are either increasing or decreasing in the same direction, then it constitutes the example of positive correlation. Let's see negative correlation. Here r is less than 0. In the first example, we can see that as x is increasing, y is decreasing, and in the second example, x is decreasing but y is increasing. So here, one of the variable is increasing and the other is decreasing, or vice versa. Thus, it forms the negative correlation. And when we plot the graph and get the scattered points, then there is no correlation and hence r is equal to 0. Now let's see simple, partial and multiple correlation. When only two variables are studied, it is a problem of simple correlation. For example, yield and plant height. When three or more variables are studied, it is a problem of either multiple or partial correlation. In multiple correlation, three or more variables are studied simultaneously. For example, yield, plant height, flowering, number of tillers. Whereas in partial correlation, we recognize more than two variables but consider only two variables to be influencing each other, the effect of other influencing variables being kept constant. For example, considering yield and number of tillers and keeping plant height and flowering constant. Now let's discuss linear and non-linear or curvilinear correlation. If the amount of change in one variable tends to bear a constant ratio to the amount of change in the other variable, then the correlation is said to be linear. For example, here we can see that in case of variable x, the values are at an interval of 10 units, and in case of the other variable, that is y, the values are at an interval of 70 units. Thus, the ratio of x is to y is 1 is to 7, that is constant ratio, and hence it gives a straight line, thus giving linear correlation. Now let's see non-linear correlation. Correlation would be called non-linear if the amount of change in one variable does not bear a constant ratio to the amount of change in the other variable. For example, here we can see that in case of x variable, the values are at an interval of 1 unit, whereas in y variable, the values are at different units. Thus, there is no constant ratio, and hence it gives a curve that is non-linear correlation or curvilinear correlation. Now, let's see methods of studying correlation. There are 4 methods for studying correlation, namely scatter diagram method, graphic method, algebraic method, and rank method. Let's discuss it in detail. Let's begin with scatter diagram method. If all the points lie on a straight line rising from the lower left-hand corner to the upper right-hand corner, correlation is said to be perfectly positive. Example, volume and weight of metal. Here, R will be equal to 1. We can see in the given plot that here we get a straight line rising from the lower left corner to the upper right-hand corner as defined. So it gives the example of perfectly positive correlation. And if all the points are lying on a straight line falling from the upper left hand corner to the lower right hand corner, correlation is said to be perfectly negative. For example, pressure and volume of gas. Here R is -1. We can see in the given plot that we get a straight line falling from upper right hand to lower right hand corner as defined. If the plotted points fall in a narrow band, there would be a high degree of correlation between the variables. As we can see in both the plots, here the points are very densely located, hence it forms high degree of correlation. Now let's see graphic method. When this method is used, the individual values of two variables are plotted on the graph paper. We thus obtain two curves, one for x variable and other for y variable. By examining the direction and closeness of the two curves so drawn, we can infer whether or not the variables are related. If both the curves drawn on the graph is moving in the same direction, either upward or downward, correlation is said to be positive. On the other hand, if the curves are moving in opposite directions, correlation is said to be negative. Here we can see that in first plot, both the variables x and y are moving in same direction, that is they are increasing, hence it forms positive correlation. Whereas in the second plot, we can see that the one variable x is increasing but the variable y is decreasing, hence they are moving in opposite directions, thus it forms negative correlation. And let's see the third method, that is algebraic method. Karl-Pearson coefficient of correlation. Here rho for population and its estimate as R for sample indicate Karl-Pearson coefficient of correlation. Correlation coefficient is a measure of intensity of association between two variables in a bivariate population. Notationally, it is written as R is equal to summation small xy divided by in the root summation small x square into summation small y square, which is equal to covariance xy divided by in the root variance x into variance y, which is equal to spxy divided by in the root ss of x into ss of y, where summation small xy, small x square and small y square can be calculated with the help of given formula. Now let's see the properties of correlation coefficient. Correlation coefficient is a pure number, that is, it has no unit. The correlation coefficient ranges from -1 to +1. The correlation between two variables is known as simple correlation or correlation of zero order. It is not affected by coding of variables. That is, correlation coefficient is independent of origin and scale. Hence, adding or subtracting a constant to all the variables or multiplying or dividing a constant to all the variables will have no effect on the correlation coefficient. Then, the fifth property is the relation between the correlation coefficient R and the regression coefficients byx and bxy is R is equal to in the root byx into bxy. Sixth property is that if the two variables are independent, the correlation coefficient between them is 0, but the converse is not true. Then, if rho or r is equal to 0, it shows that the relationship between the variables x and y is not linear. Further, the sign of r will be same as that of byx or bxy. Then, the relationship between the correlation coefficient with the regression coefficient is beta yx is equal to rho sigma y upon sigma x, or beta xy is equal to rho sigma x upon sigma y. And the 10th property is the arithmetic mean of the two regression coefficients beta yx and beta xy is greater than or equal to the positive correlation coefficients between the variables x and y. That is 1 upon 2 beta yx plus beta xy, that is average of the regression coefficients, is greater than equal to rho, that is correlation coefficient. Now let's see test of significance of correlation coefficient in stepwise manner. The first step is comparison of sample R with population value. Here null hypothesis H0 is that rho is equal to 0. That is, variables are not associated. And alternative hypothesis is rho is not equal to 0, that is, variables are associated. Second step is fix the level of significance, which is usually 5 or 1% level of significance. Step 3 is to calculate correlation coefficient R with its usual formula. Step 4 is to calculate statistic T and standard error of R using the given formula, that is T is equal to modulus of R minus rho divided by standard error of R, where standard error of R is equal to root of 1 minus R square divided by n minus 2. Hence T is equal to modulus R minus rho divided by 1 minus R square divided by n minus 2 in the root. Thus T is equal to R into root n minus 2 divided by in the root 1 minus R square. Under the null hypothesis, rho is equal to 0. The final step, that is step 5, is conclusion. If calculated T is less than table T at 5% level of significance and n minus 2 degrees of freedom, then H0 is accepted. Acceptance of H0 indicates that there is no association between two variables under study. Whereas if calculated T is greater than equal to table T at 5% level of significance and n minus 2 degrees of freedom, then H0 is rejected. Rejection of H0 means there is an association between two variables under study. Now let's see rank method. The Karl Pearson's method is based on assumption that the population being studied is normally distributed. When it is known that the population is not normal, or when the shape of the distribution is not known, there is a need for a measure of correlation that involves no assumption about the parameters of the population. This method was developed by Charles Spearman in 1904. It is also known as Spearman's rank correlation after his name. It can be notationally written as Rs is equal to 1 minus 6 summation di square divided by n into n square minus 1, where di square is equal to square of difference of rank and n is number of pairs. This measure is especially useful when quantitative measure for certain factors cannot be fixed. For example, to measure the relationship between the rankings of stock prices or returns over time, or to study the correlation between the ranks of students' performances in different subjects or standardized tests. you for joining me on this journey through our 17th unit, Correlation. If you found this unit helpful, don't forget to like, share and subscribe to Statistics for more insights and clarity on statistics. Your support helps us continue creating content that makes complex topics simple and accessible. Follow us on Instagram and LinkedIn.